All right, so where we were discussing, or we are in the process of discussing the question of regulated power supplies. And last week, you remember, we started off with, well, the basic rectification and unregulated supplies, and then later on we added the concept of some feedback and a feedback regulator in it, and we landed up with this configuration here, which was the last thing that we looked at. And it is a general sort of block diagram for a series feedback voltage regulator. And remember, why we say series feedback is because, first off, they get my pen here, that the series, because the series element here, which in our case is a transistor, is in series with the load. That the current from the unregulated power supply passes through the element to the load. So it's in series with the load, right? So this is a series regulator. And feedback, because we spoke about that, what we are doing is that we are sensing a part of the output voltage. This is whatever they regulated. This is what we require or desire. We are picking up a fraction of it, which is this bit here that is going in, right? And the fraction is determined by these two resistors here. So it's a simple potential divider. So part of the output voltage goes into an error amp. The other input of the error amp we fix at some reference. And the difference in these two things, we drive the pass transistor. And that feedback works, it's negative feedback, as we said, because when the output tries to go up, the action of the feedback circuit tries to bring the voltage back down. And if the voltage goes down, the action of the feedback circuit tries to bring the voltage back up. And the configuration that we looked at last week, where we ended, was the all transistor version. So we have the pass element here that carries the load current, and we have the error amplifier being made up of transistor TR2. The input of the transistor here is the base, so that's in the negative input. The positive input of the amplifier, we are clamping at the emitter of the transistor, and the collector of the transistor is the output of the amplifier here. And we went through the analysis and design of it, and we saw how what we basically do is to try to control the voltage at this point here, so that if the voltage output for some reason tries to climb, we bring this voltage back down, because if we bring this out, remember, this voltage at this collector plus the VBE is V out, right? And if the voltage for some reason at the output drops, we increase the voltage here to bring it back up again, okay? Just a comment too about the behavior of the circuit. This transistor, we computed some values last week, and sort of the transistor has to dissipate a bit of power depending on how much current you're transmitting through it and how much voltage is across it. But essentially, what this whole regulator does is to make this voltage here immune from this voltage here. So this can be going up and down in all sorts of forms and fashions. This here remains quite steady. And all of the fluctuations basically are absorbed by this transistor here. All right, so if the voltage suddenly gets very high on the input here, the output here is held constant, so that the voltage difference across the transistor goes up, and it has to dissipate more power, so it dissipates more heat, and that is how it absorbs this fluctuation here, by dissipating more heat. All right, just something to note. And then what we observed though is that this bit here, this error voltage amplifier, is in fact perfectly suited to a device that you met in year one called the operational amplifier. And the operational amplifier is simply a 3-terminal, it's an integrated circuit, so there's a lot of circuit elements inside of it. It's basically has 3 active terminals, one an inverting terminal, one a non-inverting terminal on the output. And of course, you have to supply voltage to it through plus VCC and minus VCC, usually. Although under certain applications, you can supply it between plus VCC and ground. And we will talk about that in some later lectures. All right. But basically, one of the things about it, so you have the op amp, and then there were 2 configurations of the op amp in use. One was the inverting amplifier, And what the inverting amplifier did, you grounded in the positive or non-inverted terminal, and you sent a current through the inverting input through a couple of resistors, R1 and R2. And what happens is that whatever you put in inside of here was amplified because of the ratio of R2 and R1, but on top of that was inverted. So instead of this, what you would actually get coming out would be this, right? An inverted version, an inverted amplified version of what went in. And then the variation on that we had was so this here was, let's go back and get my ink here. So this is plus VCC here. Then the other version, and get rid of this. The other version now is what we call the non-inverting mode. And what we do in that case is that the same 2 resistors we have here, we ground the inverting input and we put the input here. So you put V in here, and whatever V in is, you get an amplified version of V in, but it is not inverted. So it's in the same phase. Okay? Everybody remember that? And in any case, what I've done is that I've put the handout for you online so that you can read it through and refresh yourself about how that operates. The other thing about it is that one characteristic or a couple of characteristics I should say about the op amp are that one, the open loop gain. So if this is the amplifier here, AV, the open loop, if you take out all these resistors and so on, the open loop gain is huge, it's very big. And the other thing is that once the op amp is operating, it tries to keep this voltage, these 2 voltages equal. So in other words, if I put V in at the non-inverting input, the amplifier, because of its open loop gain and feedback, tries to make here also equal to V in, right? And we call that particular behavior the virtual earth behavior, which again you would have, you should remember having covered it in the year 1 course. And you have the notes. So those things, the things that are immediate at least recall fairly easy are the configuration for the inverting and the non-inverting amplifiers. The fact that the amplifier has the operational amplifier has a very big open loop gain, and that there's a virtual earth behavior that exists between the 2 terminals, in that once you connect components and you turn on the op amp, it tries to make whatever voltage is at the non-inverting terminal appear at the inverting terminal. Okay? So check that. And again, if you have any issues, well, we could pick it up in class again tomorrow. So this thing now, so we have the ability to have either an inverting or non-inverting amplifier. So what we can actually do is to swap this thing out now for an op-amp. And that brings us to this particular configuration here. Notice we have what we've done. We've taken the reference voltage. So VREF, this is VREF from the block diagram. Oops, get rid of that. Right, so this point here is, get my pen. So here is VREF, where's my pen? VREF, right, whatever that Zener is. Here is the V feedback. And we now have the output. So how does this work? First off, notice that we are operating in a non-inverting mode. Okay, the non-inverting mode means that the resistors connected to the inverting input are grounded. Notice R1 and R2, right? If you neglect the transistor, basically R1 and R2 are in the feedback loop for the amplifier and they're connected to ground. And VREF is held at a positive, some sort of positive voltage. Okay, and let's see how this thing operates now. First off, because of the virtual earth behavior, which basically allows us to derive this equation here, once I turn this circuit on, notice how I have it powered right now. I'm taking the unregulated power supply, and we'll talk about that. I'm using it to connect the plus VCC of the op-amp here. I'm connecting the negative VCC to ground. So I'm only using a single polar supply for the op-amp instead of the normal bipolar supply. And then the Zener diode, I am biasing the Zener diode from the same unregulated supply here. So this is V unreg. Okay, this is not a connection here. This is not a connection, all right? So how does this work? Well, I turn it on, and let's say we have some V out here. Because of the virtual earth behavior of the op-amp, once I have VREF here, I am going to have VREF occurring at this point here. Right, so if VREF is VZ, then this point here is going to also be VZ. Fair enough? And give me feedback to let me know if you're hearing me or if you have any questions, because I can't see the chart. So if here is VZ, then using the simple potential divider rule, we can calculate that V out is in fact VZ into 1 plus R1 over R2, which is the equation for a non-inverting amplifier, operational amplifier. Fair enough? And how this works now is, again, if for some reason, remember what we're doing here. This voltage here, if this is V out, here is kept at V out plus 0.7 volts. So if this tries to go up for any reason, this point will attempt to change. But because of the virtual earth behavior, the op-amp will take corrective action to make that become VZ again. So if this tries to change, it has to be VZ. So what it does is that if this goes up, the output voltage of the op-amp is going to drop to bring it back down so that here becomes VZ again. And similarly, if the output here falls for some reason, this point here is going to fall. The op-amp has to make these two voltages equal. So what it is going to do is to send this voltage back up to try and bring this, to bring this voltage back up. So again, the same regulation behavior that we saw with the transistor is in fact taking place here as well. so that this unregulated voltage could go all over the place, but the output is clamped basically because here has to be equal to VZ, whatever reference we choose. And if here is VZ, the output must, nothing else is changing. If this is fixed, and this is fixed, the output will remain fixed regardless of what V in is trying to do. Fair enough? Yeah? Everybody following that? Make sense?
Yes, sir.
Any feedback would be good, literally.
Good, sir.
Okay, nice. Right, so a couple of things here to notice on the circuit. First off, the op-amp is supplied from the unregulated voltage. Why do you think that is? Why would we want to supply the op-amp from the unregulated voltage? Right? Remember, let's say this is our 12-volt supply here. So if I were to power the op-amp from the regulated voltage, here is going to be 12 volts. Yeah? But what is here supposed to be? For the thing to work, here has to be what? If here is 12, then here has to be 12.7 volts. So therefore, you can't supply the output of the op-amp, or sorry, the power from the op-amp with the regulated supply, because the op-amp has to produce a voltage that is a little bit higher than V out. So what you do is that you supply the op-amp from the unregulated supply. So you have a certain amount of headroom for it to play with. What about a Zener? Can we supply the Zener from the unregulated supply? Is there any problem with doing that? Yeah, no, maybe. What do you think? Or is there any particular disadvantage of doing what we have here? Remember what we spoke about with the Zener? The Zener has a IZ min to operate and a IZ max before it gets burnt out. And that's what the purpose of this resistor here. So IZ min, what we design is to make sure that when V unreg is at its maximum, right? First off, when V unreg is at its minimum, we have IZ min operating. And when VZ is at its, V input is at its maximum, we do not have IZ max flowing through. All right. So if we know that this is going, let's say 20 to maybe 22 volts for argument's sake for a 12-volt supply, right? We can design accordingly. And once we don't exceed these limits, right, by choosing an appropriate value for R, then the Zener doesn't matter. It doesn't mind if we connect it to the unregulated supply. It is safer to connect it to the regulated supply, right? Put it up here. It is safer and a better design to connect it to here because this is not going to change. So therefore, you don't have to worry about IZ min and IZ max. You choose a nice value in between here to make sure that the Zener diode operates all the time. And the Zener will comfortably just handle that current all the time. The current wouldn't fluctuate. So powering the Zener from the unregulated supply is not the best, but powering the op-amp from the unregulated supply is absolutely required. All right, and unlike the simple transistors, the simple power supply, sorry, that have no feedback, we could choose values to give the exact sort of voltage that we want. By suitably choosing R1 and R2, we can get the exact value voltage that we require, which is the subject of this particular example, which is more like a homework example than anything else, right? So it's a 12 volt, 1 amp supply. So here is 12 volts, 1 amp. So what you do is, as we said, good design probably is to pick the Zener diode to be about half of that. So you pick like a 6 volt Zener. You could pick 5, you could pick 6, you could pick 7. With this, you could actually go all over the place too, but you wouldn't want to get too close to the 12 volts anyway. But good design, it's acceptable design and good practice to pick a value for about half the output voltage. So it gives you a certain amount of room to play with. So if I pick a 6 volt Zener, I know that here's 6 volts. All right. And I go back to my equation here. This is 12. This is 6. Pick one of these. So let's say pick R1 or pick R2 to be some value. Normally, you would want these to be in the tens of kilo ohms. All right, because you don't want to, remember, if the supply is not connected to any load, this is a load here. When the supply is, first of all, when the supply is not connected to any load, you really don't want the supply expending any sort of current in these resistors here. So you want them to be relatively big. So you typically choose them to be in the tens of kilo ohms. All right. And of course, usually when you're supplying a load, because this is much bigger than the load, when you supply it, most of the voltage and the current will go across the load. In fact, most of the current, will go through the load and not in that R1 and R2 chain. Okay. So what you do for this one, you pick one. So let's say you pick your choice. Pick R1 to be, let's say 20K and calculate R2, or pick R2 to be 20K and calculate R1. Okay, and the beauty about it now is that depending, so let's say I pick this as 20K, all right, and I want to get some value for this. Let's say you get some strange value, whatever that happens to be with some decimals. You can always put a variable resistor here and adjust to the exact value that would give you 12 volts here. So you can always trim the voltage and adjust it accordingly. So that way you're able to get exactly what sort of voltage you want from here. And as he said, you could use that process now to build an adjustable voltage regulator to give you, instead of just fixed voltages that you could get from some range, some low range to some higher range as you go past. Okay? Now just some other comments here. Notice that the transistor here, what is the current that the op-amp has to supply? I have current coming here, IC, and this is IE, which is approximately equal to IC once the transistor is on. So what is IB? IB is what? For this particular transistor, and from transistor, from what you know, IB is equal to what? IB is equal to what? Come on, somebody.
IB is equal to IC over HFE, which is 100 right in this
Good.
case.
So it's over HFE, which is the current gain. Get here, which is the current gain for the transistor. So that the op-amp has to supply the base current to this transistor here. Some transistors now, depending on the type of transistor that you're using, remember this transistor is carrying all of the current and dissipating all of the power. As we said, when the voltage goes up and down, here is held constant. So the transistor is the one that has to dissipate that extra power. So if here, as we said last week, in our example, if here was like 20 volts, so you have 8 volts across the transistor and is carrying one amp, the transistor has to dissipate 8 watts, right? If you're asking it to do 2 amps, and the transistor has to dissipate 16 watts. Usually transistors that can handle, that amount of power have a fairly small HFE, right? Typically not as high as 100, maybe a few 10s and 20s and that kind of thing. So one of the things you have to be careful with if you're ever doing this in a practical design is that you work out what IB is. And if IB is more, remember the op amp like the 741 or the 309 or the 324, those kind of things that you may have met in year one. This can supply, a 741 can supply, let's say maybe a maximum of maybe 100 milliamps. So when you do your design for something, let's say the battery charger example that we kept floating around with, let's say we need about 5 amps here at about 14 volts, right? So that this now has to dissipate maybe about 30 to 40 watts. The kind of transistor to dissipate that will require the HFE for that maybe about 20, in which case the base current required may be a lot more than 100 milliamps. So you can't normally supply it by, you may have to do some extra circuit work on here. And this is where a particular device, and if you did the course before, you would have met it in one of our examples here, and we're going to talk about it as well, is a particular device called a Darlington pair. And what a Darlington pair is basically 2 transistors in parallel, right? So you have one transistor here, and the other one is fed by the first, right? So the unit itself has one emitter, one collector, and one base, but inside there are 2 transistors, one feeding the other one. And what happens, and the overall current gain for this one is typically high, is the HFE of this one multiplied by the HFE of this one, right? So HFE1 by HFE2. And typically for the Darlington transistor, that value could be like 1,000, right? It could be 1,000, maybe up to 2,000, depending on the device. So what you would see, there are other variations of this, where instead of this transistor, there's a Darlington pair on the output. And that is the sort of, the practical sort of application that you would see being employed in that case, all right? But the calculation is still the same. If I were to put a Darlington pair, right, the output, the base emitter, this is the base, this is the emitter here. The base emitter for this is 0.7. The base emitter for this is 0.7. So that for the whole Darlington transistor, the base emitter drop is about 1.4, 1.2 to 1.4 volts. All right? Okay? Any questions?
So that 1,000 that you were speaking about, what is that exactly? The gain?
Yeah, you were saying?
Excuse?
Yeah.
Okay.
Go on, you were saying, waiting to hear the question.
The 1,000, that's supposed to be the gain of the transistor or something?
That is the current gain of the Darlington transistor pair. When you put the 2 transistors connected in this form here, the current gain of the 2 transistors is HFE of the first transistor multiplied by HFE of the second. And if each of them has a current gain of, let's say, 50, or one is 100 and one is 10, you have an overall current gain for the Darlington pair of about 1,000. and it could get a lot bigger than that.
Oh, why so big, sir?
Because because of how they connected, the series connection here. You should have done that in what do you call it? Level 1. Right? If you wire it up like this, right? The current going into the base of the first transistor, HFE times that is coming out of the emitter of the first one, goes into the base of the second transistor, and HFE times that is coming out of that one. So the current gain here is the HFE of this transistor multiplied by the HFE of that one. Right? You all didn't meet this in level 1? In ECNG2011?
So we heard about it, but then delve into the darlings and here.
Okay, I will do a couple of slides for it just to make sure that you all have that as well, and we'll take it up again. There are some problem sets, and it also appeared in some past paper questions as well. All right, so no sweat. I'll make up some notes and we'll cover it as for you as well. Okay.
Okay,
right.
sir. Thank you.
All right, and this was version 2 of the power supply. Just the circuit where I'm showing that the Zener diode is powered from the regulated supply, which is better for the Zener diode. It's safer. Excuse me for a second. Yeah, sorry about that. I have a little visitor. Okay, anyway. And this is the version that I spoke about before, where this Zener diode is connected to the regulated supply. And this is a nice stable supply. So all you have to calculate for here is a Zener current somewhere between IZ min and IZ max. Okay. So let's see. Now, right. So as an alternative to designing the regulators using transistors and op-amps, or discrete components, as we like to call them, what we can also do are to buy integrated circuit regulators. In other words, a component, a device, an integrated circuit that does all of that stuff for us. And essentially, all we have to do is to provide the input and take the output, and maybe add a couple of resistors to bias it properly. And it has everything that we spoke about in our block diagram already. And one that we haven't, which is overload protection. We will come to that tomorrow. But it has the reference voltage, error amplifiers, series pass devices, and so on. And the 3 basic sort of formats that they come in are fixed positive regulators. So this will give you like a plus 9, a plus 12, plus 15, plus 5, negative, which will give you the negative versions of these, and then adjustable outputs, which typically will give you something from like approximately 1 volt up to, in this case, maybe somewhere around 35 volts. Right? So you could get any voltage that you want inside of there. They usually do not go down to 0 because you have to make some special arrangements for that. And 35 is a limit because of how much power they will have to handle. Right? And the simplest of these is a 3-terminal regulator. And you meet these, you're going to meet these in your labs, you're going to meet these when you do your 30-20 projects and so on. And it's as easy as that. It's a 3-terminal device. One is the input, 1 terminal is the input, 1 terminal is ground, and 1 terminal is the output. And that is as much as you have to do. They add some capacitors to get rid of some noise. Sometimes there's electronic noise on the line. And this is what the packages look like. If you look at it, you may have seen some of these packages already in the lab, or you will shortly. This particular type of package is about a 1/2 inch square and the back is metal. This is something called a TO220 case. The back is what you put, the back is metal. There's a metal tab here, and you put this on a heat sink to prevent it from overheating. This one is a small one. This is something called surface mount technology, right? So this now is incredibly small. This is something like about 1 millimeter square. Right, so this is if you look at it, you're going to see something looking about this size, right? Same 3 terminals, right? And the back is metal, and again, they will attach that to the circuit board, and it will be sitting on something like a little pad of copper to dissipate the heat. So clearly, the amount of power that this would handle is a lot more than the amount of power this would handle. You would find these if you ever scrap down something like your phone charger, right? If you have a non-working phone charger and you open it up, you will see some integrated circuits inside, and you will see a very small 3-terminal regulator inside of it, right? So for instance, as a typical example, the number in the series, when you go looking for them, is LM, which just stands for the manufacturer who originally made it. But the number is 78, and the next 2 numbers tell you what voltage it is. 78 is positive voltages. So like 7805, if you go to our stores, that's a 5-volt regulator. 7809 is a plus 9-volt regulator. 7812 is a plus 12, and 7815 is plus 15 volts. And then the negative versions are 79. So same thing, 7905 would give you minus 5, 7909 minus 9, and so on. And these come in this kind of case that I was telling you, the TO220 case. This is metal here. And typically, they could give you about an amp, right? If you put this on a proper heat sink, okay? And they're almost indestructible, because if you don't put it on a heat sink and it gets hot, it's going to shut off. This is the application typical regulation. You can even operate it without these, right? But these little capacitors just happen to make them work a little bit better. And when we talk about some frequency information in the other course, you'll see why those capacitors are used sometimes. But you could even ignore it. So all you have to do is to put V unreg here, like from our half-wave filtered or full-wave rectified filter supply, ground pin 2, and if this is a 7812, you have 12 volts nice coming in out of that. And inside has everything that we were talking about. It has a reference voltage. If it's a 12 volt, they would have some sort of Zener diode inside of here, right? Maybe a 6-7 volt Zener diode. This is to bias the diode so that the current is extremely constant. So instead of using a resistor, they use something to generate a very precise current. This is the series pass element, so that's the transistor, or it may be an internal Darlington pair that they have, right? This is the protection. We haven't spoken about that, but this is for overcurrent and overvoltage protection. They shut the thing down, and we'll meet that tomorrow. The error amplifier, so there's a circuit inside of there. It most likely is an op-amp type circuit that they just built into here, right? The internal potential divider here, and then a starting circuit. This normally is a little switching circuit to make sure that the reference voltage is stable before everything turns on, right? So you don't, especially if you're dealing with sensitive equipment, if this is supposed to be plus 5 volts here, you don't want, when you put 15 volts unregulated here, that for a split second, you get 15 volts here, and then it drops down to 5 volts. This circuit will hold everything inside of here off until here stabilizes and the other voltages inside of the circuit stabilize, and then give it the 5 volts coming out. And it will do that in a fraction of a second. Yeah, so very easy, right? And these are some applications you could kind of see the use of an op-amp, for instance, in this one. So you have plus V out here, and notice what we have here. What kind of configuration is this op-amp in? Inverting or non-inverting?
Inverting.
Inverting, right? So this is inverting. So it's taking V out, right? So whatever voltage here is going to invert it and send it to drive the transistor here that is connected to minus Vn. So if this is V out, this is minus Vn, it is going to, here's ground. So by virtual earth behavior, it needs to make here ground. In order for here to be ground, here has to be minus V. So as soon as this the power supply turns on and the op-amp turns on, the op-amp immediately sends this transistor negative to drive here to minus V out to make here 0 because of the virtual earth behavior of the op-amp. See? This is the kind of thing too as well that you have to be able to do as you go through as an electronics person, not necessarily here, but later on to be able to watch a circuit to understand what the designer has. Why does this circuit work? All right. And you can reason it out very easily. So as we saw, you identified that the op-amp is in inverting mode. So whatever voltage comes in is going to send the negative of it out. We have plus V out coming in, so it's going to try to send something negative coming out. All right. And notice a little difference here, right? That this is a PNP transistor instead of the NPNs that we use. Okay. We could use an NPN. There's no reason why not. Okay. Here's an adjustable regulator. So you're putting the op-amp, and here we have the op-amp. What sort of configuration you call this? Notice the output of the op-amp is connected directly to the inverting input. Anybody remember what our configuration is called? If not, you could look at how many resistors we have in the op-amp. Are there any resistors in the op-amp circuit, the feedback circuit? The output is connected directly here, so there are no resistors. So therefore, this op-amp has a gain of 1. So in other words, this is a voltage follower. And what does a voltage follower do? It takes whatever voltage is here and sends it back, repeats it out here. So this particular network here, by using a variable resistor here, this voltage is varying, and this voltage matches this one, which shifts this ground voltage of the regulator so that this voltage goes up and down. All right. And as I say, you could get 7 to 30 volts using this kind of design. All right. And we mentioned this before. If I were to go back to my op-amp design and think about this, if I wanted to make a variable voltage output here, let's say here, I wanted to go from the same 7 to, let's say, 15 volts. If I wanted to go from 7 to 15 volts here, how to change the circuit so that I can do that. Right? So think about that. There's a little homework exercise, and we can pick it up at some point in time, maybe when we're having a tutorial. So questions?
So I have one question regarding when you mentioned regarding the question of whether it was necessary to have the Zener diode connected to the unregulated supply.
Mm-hmm.
So the only reason the Zener diode is connected to the unregulated supply is because the op-amp needs to be connected to the unregulated supply. Are there any design like modifications that could allow you to connect the Zener diode to the regulated supply?
This version here, that is what I was saying. The op-amp has to be connected to the unregulated supply because this voltage here must always be bigger than this voltage here. So for the op-amp, if I were to power the op-amp from this voltage here, then the output of the op-amp can never be bigger than here. So the circuit wouldn't work. In the case of the Zener diode, however, the Zener diode can be connected to either the unregulated supply or the unregulated. Sorry, either the unregulated or the regulated supply. If you connect it to the unregulated supply, then you have to remember that the unregulated has a V high and a V low, if you like, and that once you go through that range, that you never exceed the specifications for the Zener diode, the IZ min and max, right? But so the better approach is to connect the Zener itself to the regulated supply. The Zener doesn't, all the Zener needs, especially if we pick this at about half of that, all the Zener needs is IZ min to function. So you can calculate R to give you a little bit better than IZ min. And because this voltage here will not go up and down at all, the Zener diode doesn't have to cater for IZ min and IZ max. So this is in fact a better design.
Understood. Yeah, understood too.
Okay, but the op-amp has to be connected to the unregulated side. Otherwise, it wouldn't be able to drive the voltage that the power supply requires. Okay?
Yes, sir.
Okay. Any other questions? All right, so tomorrow now we are going to have a look at the circuit protection. We've spoken about all of these things, so we know how to get whatever voltage we want and current that we want, and we can use transistors and we can use op-amps or integrated circuit regulators, right? But how do we protect the circuit from things like short circuiting? How do I limit the current coming from the circuit? And that is what we're going to spend some time in tomorrow's class having a look at. Yeah? So if that's it, I will stop sharing here and I will stop the recording.